We looked at the fundamentals of natural language processing, or NLP, the computerization of human communications. NLP converts human language into numerical vector embeddings that capture meaning and allow computers to understand us. But as amazing as this technology is, NLP still faced limitations. The transformer advantage came courtesy its architecture, the game-changing combination of encoder-decoder with the attention mechanism. We'll see how the transformer technology helped researchers overcome the challenges previously faced by NLP and how this technology revolutionized the field. Welcome to the exciting world of large language models. Now, this is one of my favorite things, the transformer and its innovative architecture and how it transformed, pun intended, NLP technology. But first, let's set the scene. Traditional NLP algorithms were able to process text data, but the models had difficulty capturing the sequence in the data. It didn't understand sequential information very well. Along comes the algorithms, RNNs and LSTMs, both facilitating processing of sequential data. RNN, or recurrent neural networks, were able to process sequential data, but it could only do so one element at a time. And this hampered their efficiency with longer sequences. They were also incapable of parallelism, a feature that allows for the processing of multiple sequence elements simultaneously. The LSTMs came along, and now RNNs could capture some of the longer range dependencies, a capability that proved essential in speech recognition and music generation. However, LSTM's capacity for parallelism was limited to only sentences of a certain length. So how did LLMs and their advanced transformer architecture base revolutionize LLM? There are two main ways. First, there was the size. These models are large, billions of parameters large. So they could be trained on orders of magnitude more data than the traditional NLP. This alone made them much more efficient. And so large language models are able to learn from a massive quantity and quality of text and code data. Secondly, in addition to the training data advantage, the models were built on the transformer architecture. The powerful GPUs and CPUs were used that improved the speed and efficiency of the processing, but more importantly, the attention mechanism solved the problem of long-term dependency required for understanding sequential data. Now, much more of the context could be captured and processed out of the data. In addition, parallelism was now possible. This allowed for simultaneous processing of the words, the inputs, and together this gave a deeper understanding of the context or the semantics that were contained in the text. And so now NLP, specifically NLU, was at a much more efficient and effective level thanks to the transformer architecture. In a similar vein, natural language generation, the other aspect of NLP, was also improved. These large language models, because of the encoder-decoder system, were able to generate context-sensitive word embeddings, and they were much better at handling long-term dependencies in the training data through the attention mechanism. Ultimately, the transformer architecture significantly enhanced NLP. It offered parallel processing, powerful computation, and scalability. Now, complex tasks can be handled with robust computation and improved performance and efficiency in learning from larger and larger data sets. I hope you have an appreciation of how LLMs revolutionized the natural language processing technology. Even though the transformer models are the superhero that came in and saved the day, the real stars of NLP are the tokens.